Okay, so today, like last week, we'll go over some questions in the back of the chapter 3. So, like again, rings of fractions and modules of fractions. So let's go over the first question. This is question number 10 in the back of chapter 3. So I'll define what absolutely flat is in a minute. So let A be a ring. Prove that if S is a multiplicatively closed subset of A, then A is absolutely flat, makes the localization of A at S also absolutely flat, and A is absolutely flat if and only if A localized at M is a field for each maximal ideal M. So absolutely flat is a condition on a ring, and there are many equivalent conditions. So a ring A is absolutely flat if every A module is flat. So they say that if every A module is flat, then they just say the whole ring is absolutely flat. And there are many equivalent conditions. One of the equivalent conditions is that every element is idempotent, meaning so the ideal generated by X is the same ideal generated by X squared. Usually it's just containment from right to left, but in an absolutely flat ring, one of the equivalent conditions is that you have an equality. So first, let's solve the first question. So if S is multiplicatively closed and A is absolutely flat, then S inverse A is also absolutely flat. Why is that true? So let S be a multiplicatively closed subset of an absolutely flat ring. Let's call that absolutely flat ring A. We have to prove that S inverse A is also absolutely flat. In other words, so if you have an element, again, I made a mistake. If you have an element Y of S inverse A, I don't know why that slash happened. If you have an element Y of S inverse A, I need to prove that the ideal generated by Y is the same as the ideal generated by Y squared. Why is that true? Well, take any element X over S in S inverse A. So I need to prove that X over S generates an ideal, which is the same as the ideal generated by X over S squared, let's say. So actually, 1 over S is a unit. So the ideal generated by X over S is the same exact thing as the ideal generated by X over 1, if you just multiply through by the inverse of 1 over S. So the ideals are the same. So let's start all over. Let's prove that the ideal generated by X over 1 is the same as the ideal generated by X over 1 squared. So let's use the fact that A is an absolutely flat ring. So let's say X is AX squared for some A in A. That's what it means for X, the ideal X to be equal to the ideal X squared. So if you rewrite X over 1, it's the same as AX squared over 1, and that's contained in the ideal X squared over 1. But then we have an equality because X over 1, the ideal X over 1 is contained in the ideal X squared over 1, but we also already know that X squared over 1 is contained in the ideal X over 1. So in our case, the ideal generated by X over 1 is the same thing as the ideal generated by X squared over 1 or X over 1 squared. They're the same thing. So A being absolutely flat means that S inverse A is also absolutely flat.
So let me ask you one thing. So how can we say X should be equal to AX squared with something?
So look here. So again, I don't have anything to write with. So X is in here, okay?
Okay, my question is, what is the assumption right now?
A is absolutely flat. I want to prove that S inverse A is absolutely flat. So you're asking why this is true?
My question is, what is the assumption to solve this question? What did you assume?
To solve the whole question?
Yeah,
or just
for a given problem. So what is the problem?
So
what do you want to prove?
Let's go back. The first part. Let S be a multiple subset of A.
Yeah, thanks. Yeah, I forgot about the question. Got it.
Yeah, okay. So we proved, so are you happy? We proved.
Yeah.
Okay, so we are done with number, so
Got it.
this is the end. So this is the last step. Here's the last step to prove number one. Let's go back. Let's prove number two. So let's prove, this time let A be any ring. So A is absolutely flat if and only if A localized at any maximal ideal is a field. So this is an equivalent condition for when A sub M is a field. So let's skip here and let's go here. So let's go left to right. Left to right. So let's say A is absolutely flat and let M be a maximal ideal of A. I need to prove that A localized at M is a field. How do I do that? So let X be an element of A. I need to prove that every ideal of A is either 0 or the whole ring. So I need to prove that every element is either 0 or a unit. So that means that either the ideal generated by x over 1 is 0, or it is not proper. It is the whole ring, A localized at M. So if x over 1 is 0, then there's an element B in A, not A excluding M, such that Bx is 0, and we're done. There's nothing wrong with that. That's good. Suppose, on the other hand, x over 1 is not 0. I need to prove that x over 1 is a unit. So if x over 1 is non-zero, then we cannot find any element that multiplies by x and gets you 0 in A without M. So that means that the annihilator is contained in the maximal ideal M that we were talking about. Okay, so next, let's say that A is flat. Sorry, remember A is flat. So that means the ideal x and the ideal x squared are the same. So x equals ax squared for some element A. If you take the difference of both sides, you have x minus ax squared is 0. If you factor by x on both sides, you have x times 1 minus ax is 0. This means that because the annihilator is contained in M, and 1 minus ax annihilates x, then that means 1 minus ax is in M. So let's move on to the fourth bullet point. If x is an element of M, then because 1 minus ax is an element of M, then the number 1 is an element of M, and that's a contradiction because maximal ideals are proper. So this forces that the element x is not an element of M. And so we have that x over 1 is a unit in A sub M, because that means you can just write x in the denominator. 1 over x is an element of A localized at M. We can just multiply through and we get 1. That's great. Okay, so, sorry, this is, I should have deleted this. Ignore, this is bad. Okay, so we prove the direction left to right. Ignore this. Any questions? Now we're gonna
Yeah, very good, very good.
Okay, so let's go to, let's go backwards. So I proved left to right. Let's prove right to left. So I'm going to say that A is not absolutely flat, and I'm going to prove that A sub M is not a field for some nicely chosen maximal ideal M. So let's go here. Okay. Sorry. No, I proved it a different way. Okay, never mind. So let A be a ring. Sorry, I made a mistake. Let A be a ring such that A sub M is a field for all maximal ideals M of A. So let M, capital M, be an A module. Then that means M localized at little m is an A sub little m module. A sub little m is a field, and so the only modules over a field are free modules. So M sub m is a free A sub m module. So free modules are all flat, So that means M sub M is a flat A sub M module. But I mean, it's already, the free module is much more powerful, but it doesn't matter. So I'm going to say that this is true for all maximal ideals little m. And so because M sub M is a flat A sub M module for all maximal ideals little m, so moving through all maximal ideals, this means that M, capital M, is a flat A module. So if you do this with all A modules, then that means that every A module is flat. So you're done. That means that A is an absolutely flat ring. So
So you use the fact that flatness is the local condition, right?
Exactly. Flatness is a local condition. It's very important. I don't think we proved that for our lectures, but yes, flatness is a local condition. So this last statement, I think I will use again in more of the questions in the exercise. Okay, so that was a nice warm-up. The other questions are much more technical. So next question. So if A is a ring, then the following are equivalent. A mod n is absolutely flat. Every prime ideal of A is maximal. The spectrum of A is a T1 space, meaning the singletons are closed, and the spectrum of A is Hausdorff. And so I guess I made a mistake. If this is satisfied, then spec of A is totally disconnected.
What is the quotient object in the first statement? A.
So, yes. So this German n was the nil radical. It's the intersection of all prime ideals, or it's a set of all nilpotent elements.
Yeah, thanks.
So there's a lot of technical work I put into trying to solve this question. It's not done perfectly, but I will show you what I did. So I tried to prove many equivalences and then make a conclusion. So let's go 2 to 3. So I want to prove if every prime ideal is maximal, then the singletons are closed. The singletons of the spectrum are closed. So let's assume all prime ideals of A are maximal. So the elements of the spectrum are just prime ideals of A. If every prime ideal of A is maximal, then for each prime ideal P of A, the set V of P, the what's the word for this set?
Zero set of P or whatever.
Yeah, the zero set of P is a set of all primes that contain P, but because P is maximal, there can be only one element in that set. But the sets of the form V of P are closed, so that singleton P is closed. So we can do this with all singletons, and so all single points are closed. Next, so let's work backwards. If all singletons are closed, so that means if all prime ideals are closed in the spectrum, then for each prime ideal P of A, we just have the closure of P is just P, and the closure of P is just V of P. So that means the only prime ideal containing P is P. And so that means P must be maximal. Okay, so let's go back. So I want to prove 1 to 2. So I want to prove A mod n is absolutely flat. Then that means every prime ideal of A is maximal. So if A mod n is absolutely flat, I'm going to make a lot of statements and then make a conclusion. So the prime ideals of A mod n are just one-to-one correspondence with primes of A, because every prime ideal contains n. So all primes of A mod n are of the form P mod n for some prime P in A. And so also, if you have two distinct primes, P1 and P2 of A, then you have two distinct primes, P1 mod n and P2 mod n of A mod n. This is clear because if P1 mod n and P2 mod n are the same, then there's some element P1 and some element P2 such that you have an equality. P1 is P2 plus n. For some P2 and P2 and some n and n. But n is already in P2, which means that P1 will be contained in P2. And so if you can conclude that P1 is contained in P2, and then switching the roles, you'll have that P2 is contained in P1. And so P1 is the same as P2. So that means prime ideals in A are preserved in prime ideals as prime ideals in A mod n. And if you have distinct prime ideals in A, you will get distinct prime ideals in A mod n. So how does this help you? So remember what we did here is here. I'm going to prove that A mod n is flat by proving A mod n sub m is a field. So let's go back to here. So we proved equality or non-equality is preserved when you mod out by n. Let's see how that helps us. So if m is a maximal ideal of A, then m mod n is again a maximal ideal of A mod n. This is just basic quotienting. So this is where I start. Suppose P is a prime ideal contained in a maximal ideal M. I claim that A mod n localized at M mod n is not a field. So you could see that by saying that ideals of A mod n localized at M mod n are one-to-one correspondence with the ideals of A mod n that are contained in M mod n. That's what happens when you mod out by a prime ideal. So in my case, I know that at least the prime ideal 0, the prime ideal P, and the prime ideal M plus n, all, I'm sorry. They're not prime ideals, I'm sorry. It's just basic ideals, sorry. The ideal 0 plus n, and the ideal P plus n, and the ideal M plus n are all in A mod n. But like I said in the first page for this question, all these ideals will remain distinct. So there are at least 3 different ideals in A mod n localized at M mod n. So that's too many ideals to be a field. So M mod n is not maximal. And so we have a contradiction. So I proved the contrapositive actually. So it is in fact 1 to 2 is in fact true. So 2 to 1, you just do the same exact thing. So if all prime
just hold on, I mean the last statement, we just need to say M quotient by n is not maximal, right?
It's not a field, so I made a mistake.
Yeah, got it.
Hence the the ring localized at the maximal ideal M mod n is not a field, and so we prove the contrapositive. So how do you prove 2 to 1? How do you prove if every prime ideal is maximal, then A mod n is absolutely flat? It's the same thing. You use this here. Use this thing again. It's the same exact proof by counting the number of ideals I have in my ring. And it'll be either 2, 3, or more, and it's the same argument. So let's go back here. So it's a very similar argument. I can prove these ideals are distinct, and therefore they'll be able to prove whether A mod n is absolutely flat or not. Okay, next. How do we prove 4 to 2? So it was something like if something is, made a mistake. I think it's 4 to 2. Yes, if something is Hausdorff, I think 4 to 3. Sorry, if something is Hausdorff, then it is a T1 space. not the other way around. Sorry, yeah. Hausdorff means T1, not the other way around. So we have to now prove 1 or 2 or 3 implies number 4. So I need to prove if A mod n is absolutely flat, or if all primes are maximal, or what was it? Or that spectrum is a T1 space, that the spectrum is Hausdorff. So it's the same thing as saying if you can separate closed sets. So suppose every prime ideal of A is maximal. If P and Q are distinct maximal ideals, we need to find basic open sets that can separate these points in the topology, in the Zariski topology. So P and Q are distinct maximal ideals, so their union generates a non-proper ideal. And so you can find points P and Q which add together to get the number 1. The rest of this is extremely technical. So from the fact that A mod n is absolutely flat, we have every principal ideal is idempotent. And so P and Q generate idempotent ideals. So let's call them E and F, such that E and F generate the whole ring, and E squared is E, F squared is F. If you let G be E times 1 minus F, then F times G is 0, and E is contained in the ideal generated by G and F, but that's the whole ring.
So you mean the ideal generated by E and F is the whole ring? That's what you mean 1, am I right?
Yes.
Got it.
And so we can then say F is contained in Q, and that means that P is a prime ideal that doesn't contain F. G is contained in P, so that means Q is a prime ideal that does not contain G, so we're done. And then also intersection is empty. And so that's Hausdorff. That's exactly what Hausdorff means. And so we're done. So this is extremely technical. I don't think this is my solution. I think I had to look up online for this. This piece is very difficult to do on your own. This is the most important key step. Very technical. And so we're done. So we proved 1, 2, or 3 implies 4. We implied 4 implies 2, and when we proved 1, 2, and 3 are all the same. They're all equivalent, and so we're done. So let's go back and see. This is a very nice condition. So
really is.
Yeah, the spectrum being Hausdorff is equivalent to A mod n being absolutely flat. And that makes sense because all the information is encoded in the prime ideals. But it's strange that the nil radical plays such an important part in the geometry of the spectrum. It's interesting. Okay, I'm getting very tired. So let's do one more question. And actually, there are other questions that are part of this step, part of this question. There's actually 8 steps, but we'll do the rest next week, I guess. So let's go over a definition. So let A be a ring and M an A module. So let's say the support of M is a set of all prime ideals P of A, such that if you localize M of P, you get a non-zero module. So let's prove these 5 distinct points. Let's prove that, first of all, let's prove M is non-zero if and only if there is in fact a prime ideal in the support of M. So how do you prove that? Well, I mean, look at number one. It's just we proved that a module being 0 is a local property last week. That's literally what number one asks you to prove. Okay, so now let's prove that the set of all primes that contain I is the same as the set of, okay, so I made a mistake. So let I be a prime, let I be any ideal. The set of all primes that contain I is a support of A mod I. And that makes sense, right? Because you would think that if you contain I, then if you localize A mod I at P, then you should not get 0. So let's say I is an ideal of A and that P is a prime ideal of A that contains I. How do you prove A mod I localized that P is non-zero? So that's the same as proving the number one, the element one, is non-zero. So if it is 0, if 1 plus I over 1 is 0, then there's an element not in P such that x times 1 plus I is 0. But that means that x is in I, but like I is contained in P, so you can't be both not in P and in I. That's impossible. So that's one direction. What about the other direction? So I proved containment left to right. Let's prove containment right to left. Let P be a prime ideal that does not contain I. So I need to prove that A mod I localized at P is 0. So if I have an element in I but not in P, then I can just multiply any element x plus I by I, and I'll get an element of I. And so this element would just be 0. So that means whatever number I divide x plus I by, I get a fraction that's equal to 0. So we're done. So let's go back to number 3. So now this is a way to show that supports behave nicely in a short exact sequence. So let's say m prime, m, and m double prime combine to make a short exact sequence. Then the support of the middle module is a union of the supports of the outside modules. How do we do that? So let's consider a short exact sequence. If m prime is 0, then we are done, because m is isomorphic to m double prime, and then the supports should be the same. So let's just say m prime is non-zero. So let's say m prime is a subset of m without loss of generality. I know it's isomorphic to a subset of m, but without loss of generality, we can just say it's a subset of it. So suppose P is in the support of m prime. We can in fact find such a P because m prime is non-zero. I claim that m localized at this P is non-zero. This follows from the fact that m prime is a subset of m, then m prime localized at P is a subset of m localized at P. And then if you have a module that's non-zero, any module that contains a non-zero module would also be non-zero. So we're done with that aspect. Now let's say m double prime is non-zero. So it's the same thing. So if it was 0, then m prime is isomorphic to m, and we're done. Let's start over. So like Q being the support of m double prime, I claim that m localized at Q is non-zero. So why is that true? This follows from the fact that all elements of m double prime sub Q are of the form f of x over s for some x in m, and s in A, not in Q. If m is 0, then all those numerators will be 0, and there's just makes no sense. So we proved right to left. We proved, I think we proved right to left. So let's finish the other side. So let's start here. So let P be in the support of M, and assume that P is not in the support of M prime, and P is not in the support of M double prime. So let's say P is in here, but P is not in here, and P is not in here. I want to go for a contradiction. So let's say P is in the support of M, but P is not in the support of M prime, and P is not in the support of M double prime. Okay, so first of all, we have x over 1 has to be non-zero for some x in M, because M is non-zero. I'm sorry, M sub P is non-zero. That means that the annihilator of x has to be fully contained in P, or else x over 1 is 0, which it's not. So let's say you have f of x, right? You have x in M, you have f of x in M double prime. Now look at the fraction f of x over 1. Because M sub P double prime is 0, f of x over 1 has to be 0. So there's an s in A, but not in P, such that s times f of x, which is the same as f of s times x, is 0. So that means Sx is in the kernel of f. But that kernel is M prime. It's just M prime. So that means that because M prime sub P is also 0, then if you take the fraction Sx over 1, that's 0. So there's an S prime in A, but not in P, such that S prime S times X equals 0. But S prime S is an S, but that means X over 1 will be 0. That's not true. That's a contradiction. And we have a contradiction. So that means that we proved right to left is true. We assumed left to right is not true, and we had a contradiction. So this is true. We're done. Let's move on to number 4. So let I be some indexing set, M being the sum of a family of ideals Mi. I want to prove the support of M is the union of all the supports of the MIs. That sounds natural. Let's prove it. So let M be a sum of modules Mi. Let P be a prime not contained in any of the supports. So that means if you localize all the MIs at P, you just get zeros. So an element of M is of the form x sub I1, x sub I2, plus x sub I3, all the way up to x sub IN for some elements x sub ij and m sub ij. I don't know what they are. But that means x over 1, I made a mistake. This should be x sub ij. This should have an ij. X sub ij over 1 is 0. I'm sorry, no, that's true, that's true. X over 1 is 0 because for each x sub ij, there is a corresponding s such that the product is 0. If you multiply all these s sub ij's together, you get one big element of s, and that eliminates s because that eliminates this term, that eliminates all these terms, and it eliminates this, and you get 0. So m sub p is 0. So we prove that if you are not in here, then you're not in here. So we proved left to right. So let's prove right to left. So let's start here. So let's say so let's say P is a prime contained in the support of Mi for some I. It can just be one Mi. Mi is a subset of M. So that means Mi localized at P is a subset of M localized at P. And so you have a non-zero subset, and so you have to be non-zero. So we're done. That was number 4. So it's natural you would expect these answers, and so we're correct. Finally, let's say M is finally generated. Then the support of M is the set of all prime ideals that contain the annihilator of M. How do we do that? Okay, so first of all, if the annihilator of M is not proper, then M is 0. So the support is empty, which is fine. That's possible. There's nothing wrong with that. So otherwise, let's say M is a non-zero finally generated A module. That means for each prime ideal P of A, M sub P is a finally generated A module. So that means M sub P is 0, if and only if there is an S in A, but not in P, such that S kills everything, not just one element of M sub P. It has to kill everything. But that means there has to be an S in A, not in P, that kills all of M, not just M localized at P. So this part is strongest. This is the strongest part, right here. So if P is a prime ideal that does not contain the annihilator, then let S be any element of the annihilator not in P, then for each x over 1, then for each x over 1, S times x is 0 because it's in the annihilator of M. Now, we go back to saying now let P be a prime that does contain the annihilator. Then there are no elements of the annihilator in A without P because the annihilator is contained in the prime ideal P. Then that means M sub P is non-zero. So let's review. If P does not contain the annihilator, then MP is 0 because each of these terms are 0. If P is a prime that does contain the annihilator, then M sub P is non-zero. That is precisely, this statement. So if P does contain the annihilator, then M sub P is non-zero. And if P does not contain the annihilator, so if P is not in here, then M sub P is 0. So we proved right to left. If P is in here, then P is in here. And we proved if P is not in here, then P is not in here. And we proved left to right. And weird. So there are more, there are more questions following up to this question number 3.19. It has to do with the tensor product, and we will get to them maybe next week.
So when did we use the finite generation condition?
Good question. So this was a part of, I think, question number 1 in chapter 3. So this here, non-zero finally generated. MP is 0 if and only if there's one S.
Got it. Yeah,
S sub MP.
Yeah, thank you.
And therefore, if and only if there's one S such that SM is 0.
Yeah, thanks.
Otherwise, it would not be so easy. Yeah.
So you wanna finish?
I have nothing else. Go.
Got it. Yeah, thank you so much.